What's up, lads? So we're going to be going through November 2021 Physics Paper 1, and this is part 2 from the previous video, where I'll be continuing the paper and doing the last 5 questions. So we're going to start off with question 6 here, which is the Doppler effect question. So it says that a siren of a stationary ambulance emits sound waves at a constant frequency of 680 Hz. A man is standing with a detector that records the wavelength of the sound emitted by the siren, as shown in the diagram below. The speed of sound in air is 340 meters per second. Calculate the wavelength of the detected sound. So what we can do is we can use the equation V is equal to frequency times wavelength, and V being the speed of sound. So if we go 340 is equal to the frequency they give us, 680, times by the wavelength. Then we divide by 680 on both sides, and we can get a wavelength of 0.5 meters. Alright, now they say that the ambulance now moves at a constant speed along the road towards the man. The detector now records the wavelength of the sound, which differs from the previous reading by 0.05 meters. State the Doppler effect. Doppler effect is the apparent change in frequency detected between the source and the listener is due to relative motion within the medium of sound propagation between the source and the listener. Something along those lines. So 6.3. How would each of the following have changed when the ambulance approached the detector compared to when the ambulance was stationary? Choose from increase, decrease, or no change. So the distance between the wavefronts, what does that mean? That's actually your wavelength. So right now the ambulance is stationary. So it's going to look something like this, you know? The wavelength sets. But once this ambulance starts to move, because it's moving this way, it's catching up to each of the waves that it releases. So the frequency increases, and the wavelength starts to decrease. And this is all from this guy's perspective, right? So the distance between the wavefronts is going to decrease. And the frequency of the detector waves is going to increase. Now we need to calculate the speed of the ambulance. Alright, how do we even start? Well, first of all, we know it's Doppler effect, which means we're eventually going to be using the formula, the frequency of the listener is equal to V plus minus the velocity of the listener divided by the velocity of sound plus minus the velocity of the source, frequency of the source. So we know that we're eventually going to be doing this equation. But we need to manage to get the values because we're missing some values here. We know V, it's 340. We want to calculate Vs, and we know that one's 0. Fs, we know is 680. But what is Fl? That's the one that we're missing. Well, they tell us that the reading differs by 0.05 meters. How does it differ? Does it increase or does it decrease? Well, we know that the wavelength is going to decrease because the van's moving towards us. It's what I explained over here. Which means that we can say that the wavelength for the listener that the listener receives is going to equal to 0.5 minus 0.05. Okay, now that we've done that, let me just quickly calculate what that is. 0.5 minus 0.05. That's 0.45. So that's the new wavelength. But remember, that's just wavelength, okay? We want to know what the frequency is. So frequency, we can use this equation here. Frequency is going to be equal to the velocity of sound divided by that new wavelength. So this is the frequency of the listener. And that's going to be 340 over 0.45. And if we calculate that, we get 755.56 Hertz. Okay, so now we know what the frequency is. We can substitute it into this equation here. 755.56 is going to equal to speed of sound, 340. Now the plus minus thing, because the frequency has to be higher, the frequency of the listener has to be higher than this, we need this denominator, or this fraction, to be as big as possible, which means the numerator must be big and the denominator must be small. So we're going to go plus on the top and minus on the bottom. This is 0, and that is what we're calculating. and this was given to us as 680 hertz. So this is, if we simplify this further, it's going to be 340, the 340 minus that. Divide by 680. And now what we can do is we can multiply by 340 minus Vs on both sides. Now that I've done that, what I'm going to do is I'm going to divide by this term. Then we're going to subtract 340 on both sides and divide by that negative 1. And this gives you an answer of 34 meters per second. Cool, next question. So this is electrostatics. They tell us that a small neutral sphere causes a charge of negative 1.95 times 10 to the negative 6 coulombs. Were electrons added to or removed from the sphere? So it's going to be added because we came from a neutral to a negative, which means we must have added negatively charged subatomic particles. What are those? Those are electrons. So we added electrons. Now we need to calculate the number of electrons which were added or removed. That's very simply, we're going to use the equation n is equal to charge divided by the charge of an electron. We don't have to do anything funny because it went 0 to negative 1.95, so that new charge will be how much we added in. So substitute our values. Charge of an electron is on the formula sheets. And it is negative 1.6 times 10 to the negative 19. This gives you an answer of 1.22 times 10 to the 13 electrons. That looks like a 7, hang on. Okay. Next up we need to define the term electric field at a point. So electric field at a point, that is the electrostatic force experienced per unit positive charge placed at that point. Next up we need to calculate the magnitude of the electric field at a point 0.5 meters from the center of the charged sphere. So electric field, that's going to be given by E equals, and we're going to use the equation KQ over R squared. Because they gave us the distance, we won't use F over Q. That would take a bit too long. So K is 9 times 10 to the 9. Q is 1.6 times 10 to the negative 19. Remember, you don't put the signs in this equation. And then the R is, what's it, 0.5 squared. So E gives you an answer of 7.02 times 10 to the 4 newtons per coulomb. Okay, next question. 7.2. 2-point charges Q1 and Q2 are fixed at 0.02 meters apart. The magnitude of charges Q1 and Q2 is the same. That's important. And Q1 is negatively charged. So we know that Q1 is negatively charged. Okay, which means Q2 must be positively charged because there's a net force that way. If they were both negative, then the force would be this way, right? So our sphere that we negatively charged is placed at point P, 0.03 meters east of charge Q2, as shown in diagram below. And the sphere at point P experiences a net electric force of 1.38 newtons west. Calculate the magnitude of charge Q2. So I'm going to relate the information we've given to what we know. So we know that Fe net is going to equal to the F of P on Q1 plus the F of P on Q2. Now, F of P on Q1, that's going to be a negative because these are both negatives here. Right, so Q1's negative and that one's negative, which means it's going to be a negative charge. It's going to be negative K Q1 Q2 divided by R squared plus a And this is an attractive force, so it's just going to stay positive, right? K Q1 Q2 over R squared. And this is all equal to 1.38 newtons. So now we substitute our points in, right? K, 9 times 10 to the 9, and we'll call that Q2. Even though it's Q1, we're calling it Q2 because they're the same charge, remember. This distance is 0.02 plus 0.03, so 0.05 squared, plus 9 times 10 to the 9, Q2, all over 0.03 squared now. We're looking at this distance here. Alright, then if you do hectic maths by getting a denominator and then simplifying the terms you can simplify and then dividing by that, you'll get Q2 is equal to 1,11 times 10 to the negative 7 coulombs. Essentially, a nice thing about physics is you don't actually have to do any maths. If you have your calculator, you can use it to solve. If you don't have that and you can't do maths, it's alright. It's not the end of the world, because in physics they only mark this bit and that bit, and then most of the marks are there. And there's only one mark for the answer. So the majority of the mark lies in this section here. So you can still do pretty well even if you don't give any answers in your test. So that's a nice thing. So we have question 8. This is quite a tricky question. Mainly because of the way the circuit has been drawn. It's really hard to see what the charge flow is. I'll explain it to you guys now. They say that the battery in the circuit shown below has an EMF of 12 volts and an unknown resistance R. The resistance of the connecting wires and the ammeter is negligible. So we've got switch S is open, write down the reading on voltmeter V1 and V2. So on V1, if there's no current flowing, it's going to give you the EMF, because if there's no current, there can be no loss due to internal resistance. So that's going to simply be 12 volts. V2, no current can reach that point, because look at where that switch is, which means it's going to be 0 volts. Here's when it gets tricky. Switch S is now closed. The reading on ammeter is 1.2 amps, and the power dissipated in the resistor X is 5.76 watts. Define the term power. So power is the rate at which work is done or energy is transferred. And now we need to calculate the resistance of resistor X. So to do that, what I'll do is I'm going to use one of those power equations, right? We know the current and we know the power. So I'm going to use P is equal to I squared R. So the power would be 5.76. I squared is 1.2 squared. It's given. R is that. And when you solve for R, you get 4. Now when you calculate the total external resistance of the circuit. Okay, this is where I'm going to have to redraw something, because it's hard to see what's going on here. So I'm just going to redraw the circuit so it makes a bit more sense. Essentially what's happening is the current's going to flow from positive to negative, right? So it's going to go down like this. Let me draw that in blue. It's going to go down like this and pass there, like so. But here is, this section here is parallel, okay? So the current's going to split off there and then it's going to go like that. That's what confuses a lot of people. It's a parallel circuit. And then it joins together and comes past P. So in order to solve this, what we're going to say, so I've just redrawn it here to make more sense of the parallel circuit. So the current's going down here, then splits between the 6 ohm resistor and that 6 and the 2.4, and then it joins back together here, and it keeps on going. So we need to calculate the external resistance. So our external is going to equal to our series resistor, which is X, plus the R parallel branches. So let's look at what R parallel is. R parallel is going to be 1 over R1 plus 1 over R, plus 1 over R2. Okay, so what we mean by 1 over R1 and 1 over R2 is the branches. So I'm going to call this one 1, so it's 1 over 6. This is meant to be 1 over R parallel, yeah. going to be 1 over 6 plus 1 over R2, which is actually this whole branch here, 2.4 plus 6. So 8.4. It's that whole entire branch. Alright, this gives you 1 over R parallel. One over 6 plus 1 over 8.4 as 2 over 7, which if we now invert both sides, R parallel would be 7 over 2, which is 3.5. So we have the parallel resistance. So now we can get the external resistance by adding on the series, which was 4 that we calculated earlier. And that gives you 7.5. So I'm just going to move that to the top. Okay, the next question is, write down the reading on voltmeter V2. So that's this one here. Now how the hell are we going to get that? Okay, let me explain it to you. So we know that in parallel voltage stays the same, right? So whatever voltage is going through here is going to go through there. But we know also that the current splits off. The current splits to there and then it splits to there. So we want to get the current that comes through here, and we can get the voltage through. So let's start off, okay? So we can get the voltage that's going into the parallel branch by using our R parallel, the resistance there. So we can say V parallel is going to equal to R parallel times I parallel. And, well, not I parallel, but just, I, because that's what's going into the parallel branch. That's going to be 1.2 times 3.5, which is our R parallel. It's going to give us our V parallel of 4.2. So that's going to be 4.2 volts. Now what we can do is, because we know that voltage stays the same, we can calculate the current that's going through this section here, this 6 and 2.4. So I'm going to say that V is equal to I times R, and our voltage is 4.2. I is now what we're calculating, and R is going to be 8.4. So if we get I, it gives us 0.5. So now we know what the current is going through there. The current going through here is 0.5, which means I can get whatever the voltage through the 6 ohm is by using V equals IR again. And this is over the 6. So that's going to be 0.5 times 6, which is equal to 3. Okay. So it's a bit tricky to see how the pattern flows. But once you got that, it becomes easier. Next question. A length of wire of negligible resistance is used to connect point P to point Q in the circuit. So essentially what's happening is we are connecting points P and Q. So we're bypassing these two resistors, but we still have a parallel branch here of 6 and 6. So what's actually happening is we're decreasing the resistance of the circuit. We're removing this 4 ohms, so we're getting 7.5 minus 4, and we're removing a 2.4 from the external part, so that's going to be 1 over 6 plus 1 over 6, which is a third. So our new resistance is only 3. It was 7.5, so we've massively reduced the resistance of the circuit. So what does that mean when it comes to the voltmeter V1 reading? Let's think about it. Because if we decrease resistance in a circuit, so resistance going down, it means current can flow quicker. So there's more current, right? If there's more current, it doesn't necessarily mean there's more voltage. Because remember, E is equal to V times, V is equal to I times small r, the internal resistance, plus I times R external. Okay. We don't really want to look at this term because essentially what's happening, this is decreasing and that's increasing. Alright? But look what happens here. Internal resistance always stays constant, but I is increasing, which means the V internal increases. if V internal increases, V external needs to decrease to keep E constant. So what's actually happening with V1 is it's decreasing. Alright, next question. We have here an AC generator connected to a 25 ohm resistor, shown below. Coil rotates anti-clockwise. So we have to name the component that distinguishes the generator from a DC generator. That's going to be the slip rings. There's no slip rings here, it's just a normal brush, whatever they call it. In which direction will the induced current flow in section XY of the coil? Choose from X to Y or Y to X. So we're going to have to use right-hand rule. But seeing as it's quite tricky for me to use right-hand rule on the screen, what I'm going to do is I'm going to try invert this somehow. So yeah, I now have that picture. I'm going to rotate it so that I can actually move my hand in the right direction. So my first finger is going from north to south. First finger for field. Then my thumb is going to move downwards because that's the direction that the coil is moving, right? In Y to X. Y to X is going to be moving downwards according to the arrow. It's going to move my thumb downwards. And I get that my middle finger is now pointing from Y to X, which is going to be the direction of the current. So the answer is Y to X. Next up, we have the graph below shows the output voltage of the generator for one cycle of rotation of the coil. Define the term RMS potential difference. So RMS stands for root mean square, and essentially it's the AC potential difference that dissipates the same amount of heat as an equivalent DC potential difference. So it's taking an AC value and converting it into what the DC value would be. So it'd be somewhere around here. Next up, we need to calculate the RMS current in the circuit. So we got voltage, so let's start off with that. We've got VRMS is equal to, using our equations, 1 over root 2 Vmax, right? So that's 1 over root 2 times the maximum, which is 100. And that gives you 70.71 volts of RMS. Now we can use VRMS equals I RMS times R. Because we have a 25 ohm resistor in the circuit. So that's 70.71. Resistor is 25 ohms. That gives you 2.83 amps. The next question is we have to copy out the set of axis below. So the speed of the rotation of the coil is now doubled, which means our voltage is going to double and our period is going to half. Or voltage double, period half, or frequency double. Different ways to think about it. So if we want to draw this, essentially it's going to reach, we're going to compare it to the previous graph, right? So the previous graph, it reaches its maximum value at 0.025 seconds. But we know that this thing is going to shrink inwards. So 0.025 is going to be where the new minimum is. It's going to be the intercept. So if we do that real quick, and 200 is going to be the new max, it's going to look like that. And then it's going to reach negative 200, like so. It's going to go back up to 0.05. It's going to go down. And like so. And this should cap off at 200. That's how it looks like. Last question of the test, question 10, photoelectric effect. So they say that the relationship between frequency F and maximum kinetic energy, K max, of photoelectrons emitted from two cathodes, M and N, of different photoelectric cells is investigated. The graphs below have obtained from results. What did I say there? Have been obtained from the results. Okay. Define the term threshold frequency. That's going to be the minimum frequency of light needed to emit electrons from a certain metal surface. And our 10.2 is, how does the maximum kinetic energy of the photoelectrons emitted from cathode N compare to the maximum kinetic energy of those emitted from cathode M when light of frequency greater than 10.4 times 10 to the 14 hertz is shone on each of the cathodes. Choose from greater than, smaller than, or equal to. So we're looking greater than this number. So let's draw a line across and we're going to compare it at one point. So I'm going to compare it here. So there's a line. It hits there at M. And then for M, from the same point, it hits a much greater value. You can see that EK max is much bigger than for N than it is for M. So it's going to be greater than. Next up, we need to calculate the value of frequency fx indicated on the graph. So, where's fx? Fx is up here somewhere. It's the line they've drawn for us, right? So we calculate this value, and they've given us EK max. Well, what we know is we can say that the energy required to break the thing is equal to rho plus EK max. We can break this down to HF, and that F is going to be Fx, right? Rho is H4 plus EK max, which they've given us as 23,01 times 10 to the negative 19. So H is Planck's constant. We can fill that in. 6.63 times 10 to the negative 34. Fx equals H again, same thing. Now H4, that's going to be the intercept, right? The minimum frequency required. So it's going to be 10.4. And the thing was power to the 14. And then it's going to be plus 23,01 times 10 to the negative 19. So you divide by 6.63 on both sides. And you get fx to be 4,51 times 10 to the 15 hertz. 10.4. The experiment is now repeated for cathode M, using lighter frequency fx but of higher intensity. High intensity means brightness. How will each of the following be affected? Choose from increase, decrease, or no effect. So the y-intercept of the graph, not going to change, right? No effect. Because just because we increase the frequency of light, doesn't mean that the minimum frequency of the metal is going to change. The metal is staying the same. So no effect there. Next up we have the number of photoelectrons emitted per unit time. This will increase because we're shining more light on it. High intensity means more photons per second, which means more electrons emitted per second. So that's going to go up. And the maximum kinetic energy of the photon, nothing. So reason why nothing happens there is because we're not changing the frequency of light. We're just increasing the number of lights hitting. So the frequency is staying the same, which means there won't be more residual energy left over. And that's why it's no effect. And that's our paper. So thanks for watching. Remember to subscribe for more. Paper 2 will be coming before paper 2 on Monday. And good luck for your exam.